All right, so today we're going to be talking about enthalpy and more importantly about changes in enthalpy. So enthalpy, which is represented by H, is the amount of energy absorbed or lost by a system during a process. So that could be a chemical reaction, that could be a phase change at constant pressure. The pressure has to be kept constant because if you change up the pressure, it will change other things. So enthalpy is used to quantify or measure the heat flow into or out of a system because it's hard to measure that directly. So if we look at endothermic versus exothermic, whether we're talking about reactions or whether we're talking about phase changes, exothermic is when energy is given off by the system in the form of heat. It's given off to the surroundings. And so if the energy is given off, and that means your products, the enthalpy of your products is going to be less than the enthalpy of your reactants because some energy has been given off. And so that means if you look at, remember, a triangle means change. If you look at the change in enthalpy from reactants to products, it would be less than 0. So in other words, your delta H is going to be negative. Because in this unit, there's a lot of discussion about, because if we're talking about energy changes, so then you're talking about exothermic or endothermic. If it's endothermic, then the other thing would happen. If it's endothermic, then energy is going to be taken in. So that means the H of your products would be greater than the H or the enthalpy of your reactants because energy's been absorbed. So your products are at a higher energy level than your reactants were. So your change in enthalpy is going to be greater than 0, which means it will have a positive value. And that little box kind of just says the same thing, talking about endothermic or exothermic and what you would look for in regard to their sign. So a delta H of reaction, if it's positive, then we're talking about endothermic, negative, exothermic. And the negative is favored. Nature tends to wants to be toward the lowest energy. So if it's giving off energy, that's going to kind of be the favored one. So it's going to be more likely to be spontaneous. Enthalpy is not the only thing that controls the spontaneity of a chemical reaction, but it's one of the things. We're not going to really go into the other things. We do an AP chemistry, and then if you take college chemistry, you'll kind of go into some other ones. So there's different types of enthalpy, and we'll use a few. There's heat of formation, and that's a compound that it's formed from its elements at, I'm going to put this in parentheses, normal state. And what I mean by that is the elements as they exist on the periodic table. So an example of that would be hydrogen gas plus oxygen gas come together to form water. Then you would look water up and you would have a heat of formation, how much energy it either took or released to form that product. And that's what all of these are. These are all heats of formation, how much energy it took to form these different compounds. If it's negative, then it's exothermic. And if it's positive, then it would be endothermic processes.
I'm guessing the larger the number, the more energy is taken away.
Yes, exactly. But it's weird because if you think of a negative number, like if I look at like, let's see, if I look at just the first two, negative 30.6, versus negative 31.8. 31.8 is really a smaller number, right?
Yeah.
But in this case, it's more exothermic, which is a good thing, more spontaneous. Yeah. But yeah, if you took a look at your large numbers, you see there's not many positive numbers on there. If you go down to if you're on the first column, you have to go down to the bottom two before you even see any. And then once again, larger, so that 226, that means it takes more energy to make that. So that probably is not very commonly made from carbon and hydrogen. But yeah, most of them are negative. There's much more likely for there to be an exothermic reaction. If not, there's kind of like not really any reason for the reaction to occur, since things want to exist at a lower energy level. Heat of reaction is the heat or energy that's taken or given off during a reaction to form a reaction. Heat of combustion would be used if you were had a combustion reaction. So that's just if you're burning something. Excuse me. Heat of vaporization, because as we get to this end of this unit, we'll talk about different changes, phase changes. So heat of vaporization is whenever a liquid is changed to a gas. And do you think that would be an endothermic process or an exothermic process? Okay, so and it's because it's very confusing, and that's why I asked. So the way that I think about it is the liquid, the particles are moving kind of some, right? More than solid, but not as much as a gas. So if I want those particles to move more, what do I have to do? Get rid of energy or bring energy in? I have to bring energy in. So this is actually an endothermic process. And even when I teach this in AP, kids get it mixed up all the time. And I have to understand it for me, I have to go down to like the real basic level and just think, what are the particles doing? They're barely moving in liquid. Now, if I want them to move a lot, I got to take in some energy. So that would be endothermic. Heat of fusion is where a liquid would become a solid. So what do you think that one would be, endo or exo? That one would be exo. Particles are moving some with the liquid, with the solid, they're very vibrating barely, so I got to get rid of some energy. So we'll be looking at those different things. Today, we're mainly going to be dealing with heat of formation, using that for some calculations to find our heat of reaction and heat of combustion. We probably won't get to the other two things till next week. I'll be gone next Monday and Tuesday because my daughter is getting her master's, so I'm going up to Dallas. So that was another reason why I wasn't doing any more quizzes, because then if people need to re-quiz and we start running out of time and it just kind of gets a little frantic. So I counted up and we have 8 or 9 quizzes, which is more than enough for me to average together. So I decided we were good. I'm sure that's not upsetting anybody if we're through with quizzes for the year. If it really upsets you, you can come and talk to me and I'll come up with some for you.
I'm pretty sure everyone's okay with no more big tests.
No more. Well, we still got to do our one, but at least it's not the whole semester. So, okay, so we're going to be looking at what are called thermochemical equations. Sorry, I kind of ran out of room. And they're just like we've been doing. They're balanced. They show what state they are, but they also show the energy change. If you look at that, that's an example of a thermochemical equation. You can see it has a number tacked on. We haven't done that before. So that's what's included. And that number that's tacked on is the delta H, and in this case, the delta H of reaction. If the delta H is a product, like it is here, then that's an exothermic reaction. So this means that for water and oxygen to come together, for hydrogen and oxygen to come together to form water, it gave off almost 1,000 kilojoules of energy. So probably pretty spontaneous. That's why we have water. But remember that exothermic has a negative value. So if you use this in a calculation, you must make it negative, and I'll show you more what I mean in a minute. Even though it's positive here, but if it's a product and I pluck that number out and I need to put it in a calculation, I have to give it a negative sign and then use it in my calculation. If I just flip this over and write it as 4H2O plus my 967.2 kilojoules, give me hydrogen plus oxygen. Now, if I have my number as a reactant, this one would be an endothermic reaction. It takes energy for this reaction to occur. So I put that as a reactant because I'm needing it. So endothermic or positive value. So on this case, if I pluck that number out to use it in a calculation, I just leave it as it is. I just leave it positive because that's what I need. All right. We're going to look at one stoichiometry problem using this. Not doing a quiz, not doing practice over this. You will not see it on the test except in the form of a bonus. So, because we're not spending time over it, but I pray I'll make some kind of pretty good bonus with one of these for you to have a chance to do. So if I look at this reaction, potassium hydroxide, solid potassium hydroxide is mixed in water to put it into solution. So that's how I have the AQ. This is something I do all the time whenever I'm making solutions. And then it has the plus 43 kilojoules. So this means for 1 mole, because even though we don't write it, there's assumed one here, 1 mole of solid potassium hydroxide, when I put it in water solution, it's going to give off 43 kilojoules of heat or heat energy. So do you think the beaker gets warmer or colder? Warmer, it does. In exothermic reactions, it's going to get warmer. So like a hand warmer. Endothermic reaction, it's taking some heat energy in, so it actually gets colder. So like an instant ice pack. So this one would be exothermic. So this is how much energy is given off with 1 mole, but we don't have 1 mole, we have 14 grams, and we want to know what the enthalpy change is. So a little stoichiometry, you can do a lot of stuff with stoichiometry. I told my 4th period class that I know y'all are all over stoichiometry, but I personally love stoichiometry. Just like I love Hess's law, which we're doing on Friday. So I don't mind doing stoichiometry. So my given is 14 grams, but we are talking about this in terms of moles. We didn't say anything about grams. We said moles. So just as we've often had to do, I got to use my molar mass to convert the potassium hydroxide to moles. And once I do that, this is my change in enthalpy for 1 mole. So I can say 1 mole of KOH will produce negative 43 kilojoules. Since that was on the product side, that meant it was exothermic. So whenever I took it out to use it in a calculation, I had to give it a negative value. So now we just multiply across. And that 14 is going to dictate my 3 sig figs. And it's going to have a negative sign, obviously. So I got 10.7. Is that what y'all got? Kilojoules. So just a little quick stoichiometry problem. And in AP chemistry, or if you take it in college, you use stoichiometry for a lot of different things. No, that's going to count for kind of like the specific heat. With that being said, if you would have done that as 11, I would have let it go. Because there's a lot, because the numbers in this unit, I mean, you're sometimes you're calculating specific heat. Sometimes it's given to you. So it kind of gets a little bit confusing. So I usually on this unit kind of give you like plus or minus in regard to a sig fig, give a little bit more leniency on it. All right. So that was that. Let's get to what we're actually doing today more so. So we're looking at enthalpy changes, or the change in enthalpy. And the reason we do that is because we cannot measure the actual energy or enthalpy change of the enthalpy, of a substance, but we can measure the change. And that change is called the heat of reaction. So usually by measuring the temperature, we can then usually figure that in to get our heat of reaction. And the little triangle means delta, but for us, that's a change. So in this case, we're looking for a delta H of reaction. So the heat of formation, which you'll have on your sheet, is the energy needed to form 1 mole of a compound from its elements. The delta H of formation of elements is equal to 0. So elements, when they're in their standard state, and that includes diatomic, they don't have a delta H of formation. They don't need to be formed. They're already formed. Delta H of formation has more to do with forming compounds. So if you look on your sheet right here, you'll see you do not have single elements or diatomics because their value is 0. On the back, you have ions, but we will not use those. But these are ions on the back. Those are not elements. And in a minute, you'll see why that becomes important. So delta heat of formation values are found in the table, and that's why I gave you a table. This little thing that looks like a degree sign means naught, NaUGHT, and that just means that you are taking these measurements at standard conditions. For us, we'll always be at standard conditions, so it's not a big deal, nothing for you to worry about. In AP, sometimes we get out of standard conditions and then it becomes important. But for us, it's not really important right here. All right, I'm gonna move this up a little bit. So you'll see the formula that we're working toward, and it looks really scary, but it's really not that hard. It's just those big old E looking things kind of make it scary looking. So the delta H of reaction so we're subtracting between the enthalpy of the substances that exist at the end of the reaction, which would be our products, and the enthalpy of the substance that start the reaction, which would be our reactants. So in other words, we're going to total up the enthalpy for all of our products, and we're going to subtract the total of all the enthalpy for our reactants. And that's all that those big E's mean. Those just mean summation. Just a fancy way of saying we're adding it all up. If y'all haven't haven't had those in math yet, then y'all probably will as you go another year or so. The N means, as it has before, it means moles, which we will use as the coefficients will give us that. So it's pretty easy. Because if you notice on your sheet, all these values are based as kilojoule per 1 mole. So if we have more than 1 mole, then we have to take it into account. So that's why you have to have the N in there. So that's for our heat of reaction. Like I said, our heat of combustion is very similar, except it just happens to be with some type of combustion reaction. But you can see your calculation is exactly the same, whether I'm doing my delta heat of reaction or my delta heat of combustion. You're going to still do the exact same calculation. All right, let's look at a couple of these. So the values sometimes, so like for this, I'm using these values here. I think if you looked up CO2 gas on your sheet, the number's like a little bit different. See, it says 393.5 and here it's just 393. So right now we're going to stick to these numbers that we're using right here. All right, so here's my combustion reaction. So I'm finding my delta H of combustion. So what I like to do, and then we'll work it a couple of different ways. Sometimes I like to take my values and jot them down under here. So like I have CO2. So I say, okay, CO2 is negative 393.0. My water as a liquid, and water is one of the ones that's going to come liquid, gas, and solid. So they all have different values to make sure you get the right phase. It's negative 285.8. This hydrocarbon right here, negative 145.7. And there's no value listed for that oxygen. Why is that? Because it's 0, right? It's because that's its normal state that it's in. We didn't have to form it, so there's no such thing as a delta H formation. All right, so let's get started. We're going to start with our products. So the first one I have is my CO2. So I'm going to take 5 because that's how many CO2 I have, and I'm going to multiply it times its value, negative 393.0. And then I need to add that to my other product, which would be my water. And I have 6 moles, so 6 times negative 285.8. And that takes care of my products. I have everything. So from that, that's my summation of my products. I subtract my reactant. I have only one reactant, and it doesn't even have a coefficient. So it would just be negative 145 point, not one. Let's try that again. Negative 145.7. All right, so give that a try, put it in your calculator, because it's not really that hard as far as getting your numbers, but sometimes the mistakes happen whenever you get to putting it into your calculator. So I got negative 3,534.1. The reason it's that 0.1 is because at the very end, you're subtracting all of this from that, and it's places past the decimal. If you would have put negative 3,534, you'd have been fine, okay? Because I'm doing a little leeway on this. The units are kilojoules per mole. If you forget that, look on and you're using this. If you notice on here, it has kilojoules per mole. So that can be your hint if you forget what your units are supposed to be. It's also on here. So the formula looks a lot worse than the problems actually are. Did anybody have trouble getting that in their calculator? You good? All right, let's look at the next one. All right, so here's my next one. Making a little single replacement reaction. So just glancing at that one, is this reaction going to be more math work or less math work? Less. It is less. Why is it less? What would be my value for aluminum? 0. What would be my value for iron? Fe? 0. The more zeros you have, the less work you got to deal with. And then notice also the other two compounds, they don't even have a coefficient. So definitely a lot less work on this one. So we're finding delta H of reaction. It's going to be the same math work we did for delta H combustion, but this isn't a combustion reaction. So my only product is my aluminum oxide, and I only have 1 mole. And then I only have 1 reactant, no coefficient, so negative 826. No places behind decimal, so that's going to kind of be your guide. So I'll get 850, well, negative 850, I'm sorry. Is that what you got? So that one's the easy one. Y'all, that'll be the kind y'all want to see on the test, huh? The last one is going to be a little bit more work because you got to do a little bit of algebra, because in this one, you actually already have your, what we've been working on as our answer. We already have our answer. We know what the delta heat of reaction is. And we're trying to figure out the delta H of formation for that compound, C3H8. Because to get these delta H's of formation, they actually had to measure the energy in the lab. So there's not going to be a delta H of formation for every compound. So that's going to be our X. We still have at least 1 0 there with our oxygen. So to set it up, you're going to do negative 2,219.2, because that's my delta H of reaction. Then I'm going to do 3 for my carbon dioxide. So I'm going to do 3 times my carbon dioxide value, negative 393.0, plus my liquid water. So 4 times negative 285.8. Close everything out there. And from that, I'm going to subtract. Sorry, I ran out of room. I would subtract my reactant, but I don't know my reactant, so that's my X. So on this one, you're solving for your X. So that's why I said you got to do a little bit of algebra there at the end. So what did you get? What did you get, I'm sorry? 103, that's what I got, negative though, right? That's what I got too, negative 103 kilojoules per mole. Did anybody not get that where they want me to go over the math with it? Yes, okay. I'm going to erase that, Crystal, because I'm going to have to go up here. All right, so I'm going to have to work above it, okay? So when I did all of the, because whenever I did it, I had to do all that separately. I know y'all are probably better at getting it all into the calculator. So from there, I had negative 22, 1 point is equal to, so all of that together was negative 2,322. And then I still had my minus X. So I brought my 2,322 over and it became positive. And that's where you would have gotten your 103 is equal to your negative X. But then I can't leave my X negative. So that's why it ended up turning into your X is equal to your negative 103 kilojoules per mole. Because I guess you can think of that as dividing by negative 1. When you do that, then you end up with a negative 103. But I mean, trying to get all that in your calculator at one time, you don't have to do that. You can do it in a few steps if you need to. All right, did anybody else have any other questions on this one? So you'll notice in your practice, there's not a whole bunch of problems. I think like 5 or 6 or something like that. So you might have time to go ahead and do one, give one a try and check it against that given value. And you will have to use your little sheet. And then after you give one a try, we can call it a day. So tomorrow I should be back in class, but if I'm not, well, even if I am back in class, y'all are doing a Google Classroom assignment, a Gizmo. So y'all will need to do that in class. And that really has more to do with the Q formula than it actually does have to do with what we are doing today.